or minus the square root b squared minus 4ac all over 2a, right? That's our formula. We love it. And when we've done that, a, b, and c have always been what for us? Like just a number, right? A number. I plug it in, I get a numerical answer, right? We actually have a quadratic here. And I want to show it to you. This is e to the y squared minus, check this out, 2x times e to the y, and I'll put that in parentheses, minus 1. So do you see this is kind of like, if you squint your eyes just enough, this kind of looks like x squared plus b x plus c. This is a quadratic. This we call a quadratic in x, meaning x is the variable. This is a quadratic in e to the y. That's what we would call this. And I don't think anyone here has ever done a quadratic formula on something like this.
Wait,
but it's valid. Yes?
Some functions where it's like you would put like u or something like that.
Yeah, okay. So back in college algebra, when we were trying to factor quadratics, we would get these things called quadratic type. And they would look like quadratics, like x to the fourth, and then they would have like something x squared. And what you do is you do a substitution. You like u be x squared, and you would do that substitution. You could do that here. I just think that we don't need it. Like, we're beyond that. But you could do that.
It's like kind of the same logic.
Same logic, exactly. U here is e to the y. Okay? So, according to the quadratic formula, if we're going to use it, can you help me identify from this equation what a, b, and c are? So a is 1. What's b? Good. Negative 2x. Wow, b is not a number. B has a variable in it. What's c? Negative 1. Now, apply the quadratic formula. Now, remember the quadratic formula says that if you have a quadratic in x, then x will be equal to this, right? We have a quadratic in e to the y, so we are going to say on the next step, e to the y must equal, right? Not y equals, e to the y must equal negative b plus or minus the square root b squared, 4x squared, minus 4 times a times c, 1 times negative 1. So that's just going to become plus 4, isn't it? Yeah. Okay, all of that over what? 2. Holy look, we've got e to the y. There's no more y's over here, right? Yeah. We can kill this e with natural log. Can't we? But I'm not going to do it yet. Because I see this 4 here. Do you see that 4? Yeah. And that 4 can come out of those two. Yeah. And then come out of the root as a what? As a 2. It can come out here as a 2. And then this has a 2, this has a 2, this has a 2. You can cancel a 2 from everything. So we have e to the y equals 2x plus or minus root x squared plus 1. Remember, we pulled the 4 from here and here, so we had a 1 left here. Not 2, sorry. That was just x. Sorry. And then it's supposed to be over something, right? But we canceled that too. Yeah. So that's it. Now the natural log on both sides. Any questions on what I've done so far? Isn't that pretty cool? I don't know, I think it's cool. This is what y needs to be. This is the inverse function. Now, it doesn't match this one though. Because this one has plus or minus and that one doesn't. It's like they threw away the minus. Can you see why they threw away the minus?
Because you can't spell that. Natural log is negative.
Yeah, natural log has some domain restrictions. You can never plug a negative into a natural log. And if you just look at x minus root x squared plus 1. Look, if I take this plus 1 out of here, isn't that just like x minus x? And that'd be 0, wouldn't it? And natural log of 0 is undefined. But if I do plus 1 in here, then this number is actually bigger than that number. right? Because if it's not there, they're the same number. But if I add a 1 to it, this number becomes bigger. So this quantity is always bigger than this quantity. If there's a minus here, that's going to be a negative when you put them together. So we better get rid of the negative or else we're going to have domain problems. And that's this. Okay? So now you know that if you're ever trying to solve an equation, the quadratic formula can be applied even if it doesn't look exactly like the ax squared plus bx plus c, right? That if you manipulate things properly, you can still use the formula. All right, pretty cool. Now, the definitions for the rest are here on the sheet, and I'm not going to go through them. All right? Now, for each of the inverse trig functions, there are derivatives. And those derivatives are inverse hyperbolic trig functions. There are derivatives, and those are listed here. And I'm, again, not going to go through those. So what we've done today, right, is we've taken the hyperbolic trig functions, we've looked at their derivatives, we've taken their inverses, and we've looked at their derivatives. We know they all exist, and they're on a formula sheet. So if someone were to just, I don't know, on your homework, let's say, were to ask you to find the derivative of sine hyperbolic inverse of x squared plus 1. Then how would you find that derivative? Say it again?
Take what we have for sine hyperbolic.
So go find the formula for it? Is that, oh, this is supposed to be derivative. Yeah. Yeah, sorry, I meant to put the derivative up there. If you wanted to find the derivative of that, you would go into your formula sheets and you would find the formula for the derivative of hyperbolic inverse sine. What's that? 4th page. So I'll write it down up here so that way you know what I'm looking at. I'm only showing you one example of this. That's why I just want to make sure you know what I'm doing here. So I go to this page and it is on the derivatives. It's on page 5 and it is formula number 31. It says that if you take hyperbolic sine inverse of x and you take its derivative, it is negative 1 over the square root of 1 plus x squared. That looks a lot like the formula we had for the arc sine derivative from last class, but it's different. It's different. You know which one I'm talking about from last class? We actually proved this one last class. That's the derivative of that one. Okay, so this was the formula in the book, so I just need to apply the chain rule to this. So this will become equal to negative 1 over square root of 1 plus x squared, but x for us is x squared plus 1 squared. So that would be the derivative of the arc hyperbolic sine part, and then still need to multiply chain rule times 2x. All right? And then maybe just move that up here. You don't need to expand that. Okay, so you understand that? All the formulas are there. You can use them. In the homework, you'll have an opportunity to practice taking derivatives. All right. So, 30 minutes. I have enough time to get to the hanging wire now. So it turns out that if you hang a wire between two poles or something, you get this thing called a catenary. So you have, let's say, a pole, you have a wire or a rope. You know, look at, just when you drive down the road next time, you look at those utility poles, right? Those huge power lines that are draped from one to the next. All of those have a little bit of a curve to them. Those are all catenaries, all right? Turns out that all catenaries can be modeled with this function. There it is. Here, A and C are constants. So I started class, hanging this very impressive visual aid I had here, right? I hung it and I said, hey, maybe it's a parabola. Maybe it's a sine function, right? No, it's not. It is a hyperbolic cosine function. That's exactly what this is when you hang this, all right? So if I choose different values of A, I'm going to change the shape of it. If I choose different values of C, I just move it up and down, all right? Well, now I'm going to ask you a question with just that information. All right, I'm going to give you a word problem. Example here. A wire hangs from two poles which are, I want to change this problem up a little bit because I did another one the other day. I don't want to redo the same one. So I'm just going to make up my own numbers here that are 20 feet apart. The model for this wire is y equals 30 cosine hyperbolic x over 30 minus 22. See figure below. So I'm going to draw you a picture of this situation. We have two poles, and we have this wire hanging between them, like this. And in this picture, I'm going to superimpose on top of this picture our x and y axes. So here's the x, here's the y axis. So what I need you to understand is that the lowest point of the catenary is at x is 0, all right? So in this formula, if you replace x with 0, it's going to give you that lowest point. Understand? Okay. How far apart are these poles, did I say? 20 feet apart? Okay, so this is 20 feet from here to here. 20 feet. Also, this right here this is measured in feet. So everything here, x and y, are in feet. So if I go x feet, the answer will be how many feet up that wire is. All right? All right, time for the question. At what angle does the wire hit the pole? What am I asking for? The angle between the wire and the pole? Between the wire and the pole. Now, it may not make sense that's what I'm asking for, but if you need to add that to that, I'm asking for the angle between the wire and the pole. Now, what's weird about that question to start with is when we talk about angles, we usually talk about two rays, like something this way straight, like ray, and then a straight ray, and then you're looking at the angle between these two straight things, right? But I'm asking you for the angle between the pole, which is straight, but the wire is curved. So what am I really talking about, or how are we going to answer this question if it's a curved wire? Not quite. The tangent. The tangent. So imagine we could go to this point right here and do it in a different color, green. If I go right here to this point, right where it hits the pole, do you agree because this is a curve, it should have a tangent line? And if it has a tangent line, that tangent line should have a slope to it. So there's some tangent line like this, right? And what we want to find is theta, which is the angle right there. Now the angle is not the slope of the tangent line. It's not. But the slope of the tangent line should help us get the angle. So I think the first thing we should go after here is figuring out what the slope of the tangent line is at that point. And to find the slope of the tangent line, you have to take the derivative, don't you? Okay, so let's start with that. What is the derivative? Maybe I should say what we're going to do here. We first find slope of tangent line at where? At where? Like, do we know anything about this point up here? Like, at x is 10, exactly. This is our x coordinate, and 20 feet between the poles, so this is 10. At x is 10 is where we want to know. All that means is take the derivative of this, and then plug 10 in, right? Okay, so I'm going to first take the derivative. And when I take the derivative, let's see, 30 times this, right? So 30, remember 30 is just going to come for the ride. So 30 is going to come for the ride. And the derivative of cosine hyperbolic is? Sine hyperbolic, no negative, right? That was the one that was weird. Okay, so this is just going to be sine hyperbolic of x over 30. Am I done taking the derivative of this part? No, I have to take derivative of what's inside. And that's like 1/30th x is what that really means. So derivative of that's just 1 over 30. That's chain rule right there. And then derivative of this by itself on the outside is 0. And 30s cancel. And so I just need to, let me clean this up. This is just hyperbolic sine of x over 30. Beautiful. Now we plug in 10, right? So at x equals 30, or no, at x equals 10, we get that y prime would be hyperbolic sine of 10 over 30. And how do we do that?
You put it into the equation.
Yep, we just plug it into the definition of sine hyperbolic. So it's going to be 1/2 e to the 10 over 30, which is 1/3, and then minus e to the negative 1/3. And now you have to get your calculators out and do that computation, which I will take mine out and do it real quick. E to the 1/3 minus e to the negative 1/3, and then half of that. I'm getting something, but I'd like to see if anyone else is able to get it. It'll make me feel better if at least one person can get this on their calculator. Oh, one-way functions. I just erased it. Anyone? Anyone? About 0.3395, something like that? Can we just say 0.34? And the squiggly equals means approximately, right? That's not just like a cute symbol. I mean, that's a mathematical symbol. We use it. All right, 0.34. So that means that if we were to kind of zoom in on that pole, and we see that wire coming into the pole, right? That the slope of the tangent line right there, the slope of this line is approximately 0.34. Now 0.34 is a positive number, right?
Yeah.
Which means that we have some slope, right? This way? Negative number would have been this, and that we would have been worried, wouldn't we? Okay, so we have this. But that does not tell us the angle. So how can I get the angle? I'll give you another hint to kind of help you here. Let's say that I give you 2 points, right?
Yeah.
Or you know what, let me do it this way. What if I give you a point and I give you a slope? How do you get to another point on a line, on that line? I start with this point and I use the slope, right? The slope is rise over run?
Yes.
So it tells me how much to go up and then how much to go over, and then I draw a point, right? If I tell you that the slope of this line is 0.34, that means that everywhere if you were to go from one point to another, you would use this ratio, rise over run. Yes? So if I just look at this point, come down, draw an arbitrary rectangle, that's not a rectangle, triangle like that, right? If I draw that triangle, then if I label this 1 and this 0.34, then that triangle would have the same slope, wouldn't it? The rise over run would be this. And what we're interested in is that angle right there, theta, which is this angle right here, theta, yes? And can you get theta?
Yeah.
Tangent, right? You're going to use tangent because if you look at theta, this is the opposite side and that's the adjacent side to theta. So I know from this that tangent theta is opposite over adjacent. And how do I get theta? Tan inverse, both sides. So take arctan on the left. When you do arctan here, it kills it. And when you do arctan on the right, well, you get your calculator out and do it, which I'll do right here. Arctan of 1 divided by 0.34. Hold on, I had a little malfunction here. Okay, so I got theta is equal to 71.22, and then you got what? 1.24?
I got
1.243. So there are two answers. No, there's not two answers. Why do we have two different answers? One's in degrees and one's in radians, and it depends on what mode you are in your calculator. So this, I was in degree mode, so I would need to put the degree symbol there. The angle is 71.2 degrees. If you're in radian mode on your calculator, you're going to get this answer, and you do not have to put a symbol. It's understood that it's in radians. So if your answer is 71.22 and you do not put the degrees, you are incorrect. Understand? All right. So that's the angle between there. Now, why would you want to know the angle between the wire? Here's why. You know, these wires are extremely heavy, right?
Yeah.
And so if you're trying to figure out whether or not your bracket that's up there holding the wire is going to be strong enough, you would need to know the direction of the force, right? The angle of that force. And we just got it. We just resolved what the angle of that force is going to be. It's going to be, 71.2 degrees this way. So you could then compose it into like some sort of vector, and you could do other things with it in physics. Got it? All right, but you need the derivative. Let me get the sign-in sheet going. That doesn't mean we're going home, all right? Start it. Did I start that way last time? Okay, well, I'll try and switch it up, but we're all going to be here for another 15 minutes anyway. How's everyone doing? You all right? Okay? There's a word problem like this in your homework. So since I've already shown it to you, it's kind of, you know what you need to do. So I think I'm going to take the last 15 minutes here. I was going to do a problem in here. It won't be on your homework or on a test. So I think what I'm going to do instead is I'm going to talk about that one-way function. You won't be tested on this. I hate saying that to you. I should just tell you this is going to be on the final. And that way you're like, okay, I better get this down. One-way function. So you know how earlier we were talking about functions and inverses? So I think I gave you an example like y was it 3x plus 4?
Yes.
And then we found its inverse, like if this was f of x, we found its inverse algebraically to be x minus 4 over 3. So that if you plug something in here, this one will take it back to where it came from. This is an example of a two-way function. So this right here is like a two-way function. You can come up with something that will go both directions. So it has an inverse, right? A one-way function is a function where you can go in one direction, but you can't go backwards. Let me give you an example of something that's kind of like a one-way function. Not exactly, but kind of. Here's something. F of x equals x squared. So if I were to imagine taking the number 2 and plugging it in here, it would go to what? So 2 goes in there, it comes out to 4. And then how do I go back there? What would I have to do? I have to do root 2, right? But see, the problem is I could have also plugged in negative 2, and that would have went to 4. So how do you go back to negative 2? Like if you're sitting over here, and let's say you're like kind of blind, and someone says, I've got this function, and you know it spit out 4. I don't know whether or not to take it back to 2 or negative 2. Like I don't know where it came from. You see what I'm saying? If I only see the output, I'm not sure how to get it back to which of these two. You know? So this is kind of like it's possible to send it back, but I'm going to have one of two answers, right? So it's going to be like a 50-50 shot whether or not I get it. That is not exactly a one-way function. A one-way function is a function that sends something out and there's just no way back. All right? There's just no way back to it. Does that seem crazy that that would be the case? All right. Now the reason I'm sharing this with you is because of something called, and I'm going to misspell this. I feel like that's not spelled right. Cryptography? Okay. You don't know what cryptography is? Yeah, okay, so I'm going to give you a very short history. Okay? So like human beings have wanted to send messages to one another for forever, right? But messages in a way that maybe you don't hear it. It's only for this table. Like I don't want this table to hear it, right? So how can I send messages? Well, I can like write something down. I could, walk it over here. I could send somebody. Well, then they can intercept it, right? Kill the messenger, take the message, and then they know the message, right? And so there's been this battle back and forth of how to securely send messages without people intercepting them. This is what we're doing on our phones, all this hacking stuff, right? It's been this constant battle throughout history of the people trying to encrypt and the people trying to break it, right? So who do you think right now has the upper hand? Because it's gone back and forth. Like, do you remember, have y'all ever heard of the German Enigma machine? Yes. Yeah. Okay, so the Germans during World War II had this very elaborate machine that is referred to as a polyalphabetic cipher. Basically, it scrambles letters. So one of the most basic examples of an alphabetic cipher is this. And this, like you may have done like when you were like a little tiny kid. You'd be like, I want to send a message, but instead of using A, B, C, and D, I'm going to use the numbers. And so you get like, if I want to say like, 41414, right? Dad. Dad, that's my message, right? That is a very, very basic form of encryption, right? Because all someone has to figure out is that you numbered your letters. So then you could do something more clever. You could say like, this is 27, this is 1, 2, 3. So what you've done is you've shifted it. You shifted your numbering over, right? So now Dad is 3, 27, 3. And maybe they'll have a little bit of a harder time doing that, right? Okay. What the Germans with that Enigma machine were able to do is, it was basically they numbered the letters, okay, if I were to break it down real easy. But every time, they used like this typewriter that they built. And every single time they hit a letter, the next letter came from a different scrambling of the numbers. So like, you know how I had the original one was like just 1, 2, 3, 4, and then the next one I shifted it over 1? Yeah. Okay, so like they hit the first letter and it's scrambled some way. The next letter they hit is scrambled a completely different way. And the next letter is a completely different way. And the number of combinations of how many different scramblings there could be was like astronomically large. And it was very difficult for us to beat it. And you know, we had people working on it. That was the advent of computers was in that time. We tried to throw computers out. There's a movie about it. Imitation Game. They get into the Turing machine.
You had like 12 hours to break the code, otherwise.
Exactly. So we didn't really break the code outright. It took a combination of a lot of things. We had to find an Enigma machine that almost went down with a submarine. We were able to gather it, to figure out how it worked. And it had a bunch of gears in it. But the problem was like every month, the Germans would switch out the gears to a new gearing system. So nothing was ever like too long term. And there was just other things that had to happen that it all kind of lined up. And we were able to break their code finally, where we were able to intercept and predict where they were going to be, and it helped us in the war. And it came down to, on every bulletin that the Germans would release, they had a weather report. So we were able to always know what certain letters in the encryption were, and then from there kind of reverse engineer it. Okay, I'm going way off. Go look up Enigma on YouTube and you'll see all sorts of stuff. All right, or maybe Enigma machine. Don't look up Enigma. All right, so it's been this battle of encryption versus the, you know, people trying to protect, people trying to break it, right? So who do you think right now has the upper hand? The encryptors or the breakers? Think so? Let's see, let's take a vote. Encryptors. Breakers? Wow, that's surprising. It's actually not that way. It's the other way. Right now there is a form of encryption that is not possible to break. And that's like when iPhone like says that they're going to do this, and then the government's saying we want iPhone to not do this, right? It's because this encryption is right now it is rock solid. And it is called RSA encryption, or some form of what's called RSA encryption. And it's developed by three guys. You can research it also. It's a little complicated, but it's all based upon a one-way function. So let me try and illustrate how this works. It's actually pretty crazy. I'm not going to get all into the details, the mathy stuff. It's just more of the general picture. So let's say that I want to send a message to you guys, right? Just this table, and everyone else is out there listening. So what I'm going to do is this. I need to scramble my message, right? I need to scramble my message. And they're sitting there, and they're like, we're here, we're listening. What do you need? You know, what do you want to tell us? I'm like, I need to scramble it. How do I scramble it? What they're going to do is they're going to tell me a certain number. Okay, they're going to, and everyone in here can see the number. Okay, everyone, you give me this number, right? And once I get this number in some way tells me how to scramble. Does that make sense? Yeah. Okay, so they give me a number. I use that number to scramble. Once I scramble it, I send them the message. Everyone in here can see this scrambled mess, right? So you can all get this scrambled mess. If you try and unscramble it, you're going to need to somehow understand how it was scrambled, right? Well, the way it works is that number they gave me, you need that to scramble it, but to unscramble it, you got to break that number down. I'm getting off. Let me do it this way. Let's take the number 15. All right? Is that a prime number? No, it's what we call a composite number. It's made up of two numbers, right? 3 times 5. Okay? So, let me get back to that. You're sitting there, you're telling everybody, 15, all right? Everyone here's 15. So I take 15, I get my message, I scramble it up. It is now scrambled, right? The only way to unscramble this code, the only way, is if you knew that 15 was 3 times 5. But you know that. Everyone knows that 15, right? You all know, everyone knew it. So everyone would be able to unscramble the message because we all know 3 times 5 is 15. Yes? That's the way the encryption works. But this number 15 that they're yelling is not 15. It is a 40-digit prime number. So this is a 1-digit prime number, right? Yeah. Imagine a 40-digit prime number and another 40-digit prime number multiplied together to give you an 80-digit prime number. You use that to scramble. Now you send it back. The only way to break the code is if the person listening out there knows how to take that number, that 80-digit number, back to its two 40-digit primes. And you may think that's easy, but it isn't. It's so difficult that the standard is that, you know, why are we using 40-digit numbers? Why not 20-digit? You know? The standard that these guys, the RSA encryption is based upon is, they say, okay, let's look at how many computers are out there. Let's look at how many the processing speed, the average process, you know, supercomputers, take everything out there. If the entire planet was to turn every computer on and say, go try and break down this 80-digit number, it should take, I think the standard is 10 times the age of the universe is how long it should take for the computers to hit it. Does that make sense? So if computers get faster, you just go with bigger numbers. You go 50 and 50, 60 and 60, 100 and 100. And you're never going to run out of primes because there are an infinite number of primes. And it's hard to find them. You can't just like go and just pick a number and go, oh yeah, it's prime. I mean, they're spaced out and weird. So this is what I meant by one-way function. You've got these two numbers, right? You multiply them together, and it gives you this 80-digit number here. There's no way back. There's no algebraic way. There's no like, okay, take it, divide by this, do this. There's no algorithm to take it back. You just have to guess. Guess. And that's what computers would do. They just keep guessing, trying to get the two primes to work, and it just takes too long. So right now, you know, when you hear on the news and things like that, like, you know, the phone is encrypted. Now there's different levels of encryption, and RSA encryption is by far the strongest, right? Or whatever, they've even made this better. But when they say something they can't get in, like I used to believe like, no, you know, the FBI, they can get in. The NSA, right, National Security Agency, oh, they've got ways in. Not with this encryption. There's just not a way in. So, you know, there's been some things in the news where they talk about